Welcome everyone to the Astronomical Society of Edinburgh. My name is Mark Phillips, the president, if you don't know who I am, and I haven't met very many people since we've been online in the last couple of years. So this is our second meeting back since lockdown. So hoping it goes well. We've got lots of new technology that we're working with, and lots of people pulling strings behind the scenes and doing a great job. This is what we've got coming up tonight. We'll just have a few slides first of all, and then we'll get on to our main speaker for the evening, Dr. Justyn Campbell-White from the University of Dundee. And then after that, we've got Alan Pickup, who will do an update on what's in the sky in November as well. But welcome. Is it coming through? Yep, coming through, okay. All right, okay, thank you. So welcome wherever you are. We've got lots of people in the hall here. We've got people, ASC members on Zoom, and we have a number on YouTube as well, visitors. So welcome wherever you happen to be. I thought I'd give you a couple of updates for members. We were going to have some lapel badges here for you to buy tonight, but unfortunately Andrew can't make it, so they'll be available at the next physical meeting, £5 each, and they're really quite smart if you want one of those. We've had a request from various people now that we're out of lockdown to do some group observing sessions. So if that is something that interests you, let me know. Maybe we'll set up a WhatsApp group. There will obviously be short notice notifications because of the weather. But if that is something that you would like to do, be involved with, going out observing somewhere with the telescopes and learning from each other, then please let us know. For members, renewals were due on the 1st of October. We're doing pretty well for renewals. It always takes a bit of time, but if you can renew, that will be quite good. You don't want to miss out on all the exciting things happening in the society. I thought I'd say a bit about a membership, since there's a lot of people who don't really know who we are. It's only about £30 for a full or £50 concession. We've had a bit of a renaissance over the last couple of years and grown to 154. And I think that's probably the biggest that the society's ever been. Lots of stuff going on and lots of people learning from each other and doing some very interesting things, which I'll show you soon. We are local to Edinburgh, but we do have members actually from all over the world. You have a few in Europe, as well as a few in England as well. But we are mostly Edinburgh-based, but we do welcome members from everywhere. You can buy a gift membership for someone if you want to do that as well. We have a lot of interest in that. As a member, you can join these meetings physically, as visitors can, but also on Zoom if you'd rather do that. We have a very active imaging and observing group where people talk and learn about how to image the night sky and what to observe, and just learn from each other, as I said. You also get a weekly email newsletter that's usually weekly, and that can contain anything from just what's happening this week, the general updates, what's in the sky, observing challenges, recent images, things like that. Maybe some more esoteric discussions like we've had recently, which are mostly rambles around my brain, I think. As a member, you can also take part in any member-only observing and events as well. We do have public events, but we hope to have member-only events. And we have telescopes that you are welcome to borrow and try out as well. Here's the sort of thing that our members have been doing recently, just a quick montage of some of the most recent images. And I think you can see there's some talented images in our society now, and the amount they've actually come on from when they started is quite staggering. So if you look on our Flickr page, you'll see loads of images like this. And if you want to stay in touch with us, we have a website where everything goes on, Facebook page, Twitter, and all our meetings that we've had over the last couple of years are on our YouTube channel, as will this meeting be as well. So you can catch up on a lot of stuff there. These are the meetings we have coming up in the next couple of months. For members only, next Wednesday, we have our imaging observing group. On the 19th of November, we have the famous David H. Levy. He's going to give us a talk from the USA about his life in astronomy. Our own Will Joy will give us a chat here in Edinburgh on finding space rocks, hunting for meteorites. The 17th of December, we'll have a talk about Thomas Cook, the telescope maker. We have interest in that we were very involved on Calton Hill, where there is a Cook telescope. First talk of the new year is about Neville Masculine, and that's from Rebecca Higgett from the National Museum of Scotland. And we also have, on the 21st of January, talk by Dr. Elizabeth Stanway on building galaxies one star at a time. We have other talks lined up as well, but those are the ones of the next few months. So over to Justyn. If you want to come up, Justyn, and plug in. I haven't met Justyn until tonight, but I know Justyn from the Hoyes project, which some of us have worked on as well, and Justyn's been involved in that, and is one of the co-leads, I believe. Yeah. So I think maybe Justyn will tell us a bit more about the Hoyes stuff as well from his talk. Okay, over to you, Justyn.
Okay, and is that volume okay? Everyone can hear me all right? Great. So yeah, thank you very much, Mark. Yeah, it's great to be here. Great to be here in person, giving a talk, which I haven't done for a while, and good to be online as well. So I'm Dr. Justyn Campbell-White from the University of Dundee, where I've been for the last just over 2 years working on my postdoc there, which I'm going to tell you a bit about tonight. So this is work funded by the STFC, the Sciences and Technologies Facilities Council, and the PI for this work is Dr. Aurora Cecilia Aguilar. And so before that, I did my PhD at the University of Kent and graduated in 2019. And as Mark said, that's how I've met him as part of the Hoyes project, which you know a bit about here. So I'll give you an update for that later. So just move that a little bit. So the outline of this talk this evening is I give a quick overview on star formation and 3 main sequence stars to put into context what it is the work that we've been doing at Dundee. And then I'll talk a little bit about stellar spectroscopy and how we obtain the data that we've been analyzing. And a lot of the work over the last 2 years that I've focused on was designing some analysis software to be able to analyze a lot of data that we have for these stars and more that we're going to be getting. So I'll show you that and give you a demonstration of the software and talk to you, show you the results that we recently obtained with the code and what's left for my position here and my future research in this field, and then quick update on the Hoyes project as well. So jumping right into a very brief overview of star formation here. So I'm sure a lot of you are quite aware of this. I'm just making this a bit bigger so I can see it. Here we go. Great. So in a star-forming galaxy like our own, around the spiral arms, you get molecular clouds and dense areas of gas and dust in space. And through perturbations, so gravity or turbulence, they start to condense and you start to get dense cores. So going around, can you see this side? Yeah, so going around this way. So you start to get these cores that then start to collapse and become, the gravity starts to take over, and from these dense clumps and cores, you start to form stars. So this happens in a clustered environment. So stars form together, one another. And then the stage that we're interested in is either the pre-main sequence or the young stellar object phase. So I'll probably just say young star throughout the talk. But this is the stage where the star has started to fuse hydrogen. So it's giving off light, and it's still actually gathering the last part of its mass from the disk. So due to the conservation of angular momentum, as the star's spinning, all of the material that's still around it condenses down into a disk. and it's from that disk that the planets start to form. So that's why in our solar system, for example, all the planets are in what's called the orbital plane. So that comes from this stage of the star formation. And as the star gets its last bit of matter from the disk, that's also going to affect how the planetary system is going to turn out. So this is a very important part of the star's lifetime before it just reaches the main sequence and carries on its life for a star. So in terms of an age range, if you think that these stars, so similar to the sun, they're going to live for billions of years, tens of billions of years. And at this stage, they're a few millions of years old. And although that sounds like a very long time to us, comparatively in a star's lifetime, if you compared that to our lifetime, they are actually just a few months old. So they're baby stars. So that's the part that we're interested in. And then, yeah, the final stage is your main sequence star with your planetary system there. So there's a nice animation from ESA, the European Space Agency, that shows sort of what we think is going on at this stage of star formation. So you have the star in the center there, and those bits, those channels that are going onto the star are going along the magnetic field lines, which are very prominent for these young stars. Just play it again. So, and all the material there is in the disk, and it's from this disk that the planets will form. And this very central part that you see there, where the material feeds onto the star, that's something that we're particularly interested in with the work that we're doing. So we do know that these stars have their disks around them because we are actually able to image them now. So this is sub-millimeter continuum images from the ALMA array. So this is false color images of essentially radio waves and collected using an interferometer. So this is from one of the millimeter arrays in Chile. And we can see from these disks that they do have quite a lot of structure, and they have gaps. And we believe that those gaps are due to planets actually carving out some of the material there. So in terms of these observations, because they're radio wave observations, sub-millimeter, they're actually tracing out quite cold material. So it's material that's quite far away from the star. And one of the questions actually is that if these rings that you see in some of these protoplanetary disks are caused by planets, what is it that stops the planets from being accreted by the star? Like, why doesn't the star sort of envelop everything as it moves in towards the star itself? How does that stop and the planets the planets end up in stable orbits around the star? But and to answer that, we need to look closer to the center of the star. So for an idea of spatial scales, if we take this animation here, this artist impression, the star is always a lot bigger than it should be in the center there. So if you imagine that this star is actually about 215 times bigger than it should be, that would put the Earth's orbit at 1 astronomical unit, sort of right about on the edge of where the star looks there. And then you'd have Jupiter's orbit at 5 AU, about here. The solar system orbit extends out across the whole of the disk there. And so the ALMA resolution that we get from these interferometry images is about out to Jupiter's radius. So it can be a bit better than that for the pre-main sequence stars that are nearest by to us. But for the overall population of stars, that's about the best we can do. So we really want a way of being able to figure out what's going on right at the center of these stars, how it's interacting with the disk. So here's another view of the protoplanetary disk and the star itself. So in the center there, you have the magnetic accretion, which is where the material is feeding along those magnetic field lines onto the star. And as that's happening, you're getting these supersonic, turbulent motions and jets that are giving off shock waves. And all of this gives off light, so very energetic light. So by looking at the light that's at visual and ultraviolet intensities, we're able to actually see what's going on closer to the star. So as you get further out, that's when you get to your infrared continuum and your sub-millimeter continuum. And again, the orbit of Earth would be sort of about here at the edge of the disk. And we really want to see what's going on in the center there. So it's also well known that these young stars are highly active in that not just the accretion, but their variability. So over time, they change their brightness. So that could be like in this artist impression you see here with material that's in the disks coming out of the disk and being warped and blocking our light from the star for a little bit. Or it could be due to planets forming, again, blocking our light. It could be that as the star is undergoing these accretion bursts, where a lot of the material is feeding onto the star, this really heats the star up and in turn makes it a lot brighter, gives off a lot more light. And that's so there are sort of prototypes for these stars that do this over a certain amount of time. It's not clear at the moment if all pre-main sequence stars are variable in this way, or if they all go through a phase like that, or if it's due to the mass of the star. So these are the questions that we're aiming to answer. So if you keep in mind as well, when we look at all these stars, we're seeing a snapshot of space. We see one star that's 5 million years old, another one that's 10 million years old. This one's twice as big as this one, but the thing is there's literally billions of them. There's so many of us to look at that's how we can piece together what is happening by all these different snapshots. So one of the ways of looking for these young stars is from the variability. So this is an optical image of a star, Assassin 13dB. And on the left is how it was in quiescence. So that just means when it's not outbursting. Sorry, on the left is the outbursting phase. On the right is when it's in quiescence. So you can see that the colors of the other stars are also the same, but this one also changes color while it dims. And one way of checking how this happens is with the variability of the light curves. So what you see here is a graph of time versus brightness. So at the bottom of the graph is just days. So each data point is pretty much just separated by a day, so a night's observation. And on the right is brightness. And you can see that in the 2014 to 17 outburst, it got almost 2 magnitudes brightness. So that's thousands of times brighter. And then it started to dim down. So this work was also done in collaboration with the HOYS project. So the HOYS is ongoing photometric monitoring project of these variable stars that I know you've heard about before here. And what our project does is actually use the spectroscopy of these stars and looks at the variability of that to try and probe right into the inner disk as well. So it's been well documented for a while now that these pre-main sequence stars have a lot of activity in their stellar spectrum. And a lot of my work does focus on this. So before I get too far into what's happening with the spectra here, I'm just going to give a quick overview of spectroscopy. And I saw that, I think it was a few months ago now, you had a talk here on stellar spectroscopy, and it was very comprehensive. I'm sure a lot of this will be very basic for some of you now that saw that. But just to give you the overview, in case you didn't see that one. So spectroscopy is the study of how light interacts with matter. And it takes advantage of some of these different transmission properties of light to essentially figure out the properties of the light, but also the matter that it interacts with. There are 2 main ways of obtaining a spectra, either by a prism, so like the Pink Floyd album, where you take your white light and shine it through a prism and split it up into the rainbow colors. The other way is through diffraction grating. So this is like what happens at the back of the CD, or if you shine a light, you sometimes see it with even just a small sliver of light through your curtains at the window, and you start to see the rainbow pattern on the opposite wall. And a lot of spectroscopes use a combination of both prisms and diffraction gratings, or grisms. And a lot of digital spectroscopes use fiber optics to transmit the light. You can also use mirrors to help disperse the light further. So a combination of these techniques are what are used in telescopes to be able to take a spectra of a star. And so what do we mean by spectra of a star? Well, if you have your source and you have your spectroscope from your source, and that source is just giving off continuum broadband light, When you split that into the optical colors, you get the rainbow prism that you see there, rainbow pattern. If you then put some material in the way, in this case, this is just hydrogen gas, you then get an absorption spectrum. So this is where the hydrogen molecules are absorbing the light at a very particular wavelength or color. And that's blocking out some of the light that you see from your rainbow pattern. And then vice versa, if you were to take a spectroscope and look at that gas, because that's absorbed the light at those very specific wavelengths, it's also then giving the light off at those wavelengths as well. So then you get emission spectroscopy. So it's mostly emission spectroscopy that we're going to be focusing on here. Similarly, if you do this for space with your telescope, in this case, in the diagram there, you have a gas nebula in the middle that's blocking out some of the light, and then you get your absorption spectrum or your emission spectrum. However, you do just get an absorption spectrum if you look at a star, and then if the star has a lot of activity or it's giving off excess emission from a lot of different materials around the star and it's hot enough, then that's what we're doing. We're just directly looking at the stars, getting the spectra. And so what can spectroscopy tell us? Well, we can actually identify which elements are giving off the light. So this comes from the theory of the atom and how you have different number of electrons per atom. And it's actually the electrons and the way that they move and vibrate around the atom that gives off the light. So you take light of a particular wavelength or intensity and it hits an atom. The electron can change energy levels or move around. And then that gives off the light again at a different or a very discrete wavelength. And you can see as you go along the periodic table and you have more and more electrons, the potential number of emission lines you can get increases exponentially. And a lot of them have been very well mapped out, and that's what we take advantage of. So even hydrogen, for example, though it just has its one electron, so hydrogen, the simplest atom, just a proton and an electron. As light comes in and hits the electron, it can change its energy level. And I'm not going to get too far into the quantum mechanics of all of this, but essentially the quantum part of it means that everything is very discrete, and the wavelengths or the color that these elements give off is very, very well categorized, such that if we take a very detailed spectra, so this is a spectra of the sun, again, all of the colors there that are gradiated, all of the little dark patches that you see, they're corresponding to these absorption lines. So that's where a certain element is absorbing the light at that very specific color. And when you translate that onto a graph, so at the bottom of this graph, you have wavelength. So this goes from about 4,000 to 8,000 angstroms. So that's the same as 400 to 800 nanometers. And all of the dark fringes that you see from the solar spectrum, these are called the Fraunhofer lines. They correspond to these dips on the graph there. And in the opposite sense, if they were emission lines, so lines that were giving off light at that exact color, then they'd be peaks on this graph at the bottom. And for a bit of perspective on the accuracy of these graphs, so this is, if you think that this is divided up into nanometers, this is like taking a human hair widthwise and slicing it up about 1,000 to 5,000 times. Once you've got your hair and it's in that many little pieces, that's the precision that we get to with the colors. And that's how we really know with quite high accuracy what elements there are in the spectrum. And in more modern spectroscopy, we do this by attaching a spectroscope to a large telescope. It doesn't have to be large, but if you want high resolution spectra, you also want to be able to collect a lot of light. So this is a photo I took from ESO La Silla in Chile, and the dome right at the back there is actually the biggest one there, houses the 3.6 meter telescope. So this is me with the telescope. The mirror is just behind it there, and it's 3.6 meters across. And then underneath is all the spectroscopes. So the prisms, the mirrors, everything that I said before that splits out the light there. And when you take an image with one of these telescopes that has a spectroscope, you are just actually doing that, like taking an image of the sky. So like when you look through a viewfinder, if you're trying to get an optical or a visual spectra, you're just taking an image like that and then usually placing a fiber optic on the star. So this is what's being done here on the computer system. You place your fiber optic on the star, and then the light just from that star will go through all of your instrumentation and prisms, diffraction gratings, until you get the image on the screen here. So this is your spectra. And there are quite a few calibration steps after this. So similar to when you do photometry, you have to do things like dark current and flat fielding. And you also then need to assign your wavelength scale to your spectra. And you end up with one of these graphs. So again, wavelengths against flux or intensity. So once you've done this and once you've obtained it for your stars, this is what we can then analyze. And this is how we're going to look at these young stellar objects or young stars. So going back to that, although we have these continuum images in nice high resolution, so this is the HR Tau one from ALMA. What we see on the right is just an optical image. So this is one from the Beacon telescope for the HOYS project. And you can see the stars themselves are absolutely tiny because they're just essentially point sources depending on your the resolution of your telescope. So the top left, if you can see that one, is just again another an image of what you'd see on the sky. We want to use the spectra, which corresponds to these high energy transitions, the high temperature, so all the things that are going on really close to the star. And that essentially allows us to shine a magnifying glass on this light to interpret what's going on there. So that brings us back to the graph here of our handful of young stars that have lots of emission lines in the spectra. So this, you only get this when you have these really high temperatures, so higher than just around the star that you'd usually have. And they correspond to a large range of elements. And when you start getting to these transitions as well, they're categorized by different atomic and quantum parameters. So again, I'm not going to get too far into that, but we can tell a lot about the elements around the stars by looking at the spectra. And then looking at the high resolution spectra tells us even more. So if you have material rotating around the star and you were to take a high resolution spectra of, example, one of the hydrogen lines, the line profile that you get from the spectra, so again, this is still just the wavelength against the intensity, you can change that wavelength into a speed, or if you take the speed, the wavelength that you expect the line to be, that's 0. And then either side of that is how much the material is moving either towards you or away from you. So this is it's the Doppler shift for spectroscopy, which is exactly the same as the Doppler shift you have like when a race car goes past, or like the ambulance going past right now, actually. So as that was very good timing. As the as the sirens move further away, it seems like the pitch of the wave is stretched out. And this is exactly what's happening with the light here. And again, this is done at a very high resolution. But these line profiles actually tell you a lot about the motion of the material around the star. So when you have this in high resolution, you can look at different material and see where it must be coming from and how fast it's moving. And that actually allows you to build up a tomographic map of the material around the star. So you can see that, for example, it might be non-axisymmetric, which means that it's only coming from one side of the star, not both. And this has been done for a few stars now. So this is the work that my boss Aurora has been doing at the University of Dundee for a few stars now. Another thing you can do is use the profiles of the lines as material moves around the star to see where exactly from the star this material is coming from. So when you have these magnetically channeled accretion funnels or hotspots onto the star, that's feeding onto the star at a very specific point. And it might be that that's very stable. It moves around with the star as the star rotates, or it could be that that's moving over the surface of the star. And it's how that material is getting from the disk to the star that is going to determine a lot of future properties of the star, like mostly how the planetary system might turn out and how if the star will remain stable. And so looking at these high resolution line profiles really allows us to see so much more than just the light. It's more having the techniques now to analyze them, which is what we do have. So as I said, this has been done for a handful of stars now. And when I started this project, part of the goal was to be able to develop some software to analyze lots and lots of data to do this for more stars. So that's what I started doing. So we had the sort of methods already there. So we knew we had a lot of spectra. We were going to get more spectra for these young stars, and we really want to be able to just go from the spectra to actually figuring out what's going on in the center of these stars for lots and lots of stars themselves. So the code that I developed is in Python, and it's called StarMelt, which is an acronym for stellar accretion mapping with emission line tomography. So emission line tomography is the method that we have there. And there's quite a few steps to the flowchart here. And since I have my computer and we checked that it was all working, I can actually give you a quick demonstration of the code rather than just go through all the slides of how it works. So I'm just going to swap over to the other presentation. And hopefully this might go a bit fuzzy. And okay, so it looks like it's okay now. So this is developed in Python, and this is run in something called a Jupyter notebook. So all the code is here in the notebook, or the Python code. And this is just a slideshow version of it. So I can flick through and just show you how it works. So since I finished developing this code as well, I've actually been using it to just carry out the research, and this is sort of the steps that we take to actually analyze these data. So the first thing to do is just import a load of Python modules and then select which star you want to look at. So these are all the different young stars that I have on the screen. I don't know how big a lot of the text is, so I'll talk you through it. What we'll do is we'll pick one of the stars that I'll show some more results for in a moment. So X loopy, pick the star and carry on. And then it then looks up the spectral type of the star in the database, which allows you to match it to a template, so a standard spectra, which will be important later. You then see what data is available for that star. So this is one that has lots and lots of archival data. So these young stars were looked at by many spectroscopic surveys because they were candidates of hosting planets. And one of the methods for finding planets is by taking the spectra of the star and seeing how it moves. It's called the radial velocity method. So a lot of these stars, as I said, have a lot of data. And what you can do here is pick the data that you want to analyze and so that you can look at it all together and compare one another. So for this, we're just going to look at data from HARP. So this is the telescope that I showed earlier. And again, there's quite a lot of instructions here because this is actually just the notebook that we use, as I said, to analyze all of this data. So the first thing that we do after we select the data is just plot the spectra. So this is the spectra as it's read in, which can be uncalibrated in intensity. So you can also see here the spectra as it's normalized. So it's all set to the same scale so that you can compare the profiles quite well. So if we zoom in over here, so this is the this is the hydrogen beta line. So this is one of the hydrogen lines that you get from the spectra. You can use this one here that has a much wider profile than all of the others. The legend's probably a bit small, but this one is from the 2008 outburst of this star. So you can see that the profile is completely different to all of the other ones. So that's something that we can tell straight away from the spectra just by being able to compare them to each other like that. The next thing we want to do is calculate the radial velocity, and the V sin I is the rotational velocity of the star. So as I said earlier, the way these emission lines are at such specific wavelengths that the motion of the star relative to us actually shifts that wavelength a little bit. So from this graph on the left here, if we're here at the sun and we take any given star, because that's going to be rotating around the center of the galaxy the same way we're rotating around the center of the galaxy, its relative motion to us is called its radial velocity, and it'll either be overall away or overall towards us, just that motion. And the way that we can calculate that is by taking a template star where we know where the lines should be and the speed of that star, and then comparing one to another and doing some maths. Again, I'm not going to go into everything there, and getting what's called a cross correlation function, and that tells you the overall radial velocity of the star. And then this is the radial velocity method for searching for planets. So if you imagine a planet is going around a star, what actually happens is the star itself also moves around a small circle as well. So this is where the combined center of mass of the two objects orbiting around a common center. And if you are taking the light from this star, the spectra, you can see that the lines, so in this case, the absorptions lines, they're shifting from left to right as the planet's moving around the star. So this doesn't have to be a planet though. The same way that we're looking at these bright emission lines that are coming from the star, so all of this really intense material that's at hot temperatures, this is also moving around the star in most cases. So we're able to use this exact same modulation, but to do this, we really do need to know the radial velocity of the star, so how much it moves with respect to us. So that's the next thing that we calculate here, and we see we already get the value there before the plots have finished plotting. But you get this curve that's just taking the template spectra and the average of all your input spectra, and where this peak lines up, the corresponding value on the graph there tells you about the radial velocity. The other thing that we measure is the rotational velocity of the star, so how quickly it's actually spinning on its own axis. And that's something that I'm not going to go into too much here, but that tells you about how much the lines should be broadened. So the next thing that we want to do with this is to be able to identify where all of the emission lines are in the spectra. So we can do that by comparing all of the peaks here to a reference database of emission lines. And we want to be able to do this automatically. So the first step in doing that is to roughly subtract the continuum from the lines. So the green curve that you see along here is the input spectra, and the red one underneath, I'm just going to zoom in a bit so you can see a bit better what I mean. The red curve underneath is the one that we're trying to get, and we want to keep it as flat as possible. So you can see that there's a little dip at the bottom of this one. So a lot of the advantages of using this Jupyter platform is that you can change certain parameters based on the data. So you can play around with it a little bit. So by changing the sampling window of this filter that goes all the way across the data, you can completely smooth out that bit and just be left with the emission line. And then the next step after that is to just pick out all of the emission lines from that smooth data and get the wavelength positions of them. So you can see here, if we go and zoom in to part of the spectra. So we've picked up an iron-2 line, a helium-1 line, a silicon line, an oxygen line. So all of this is by matching the positions of these lines to a database. The one that we used was compiled by the National Institutes of Standards and Technology, which is an institute funded by the US government. And a lot of the positions that they've done they've been calculated theoretically mostly over many years now, but it's quite high accuracy for them. So now we've got our input spectra for this star. We've gone through, we've found out how fast the star's moving with respect to us. We've identified all of the emission lines in its spectra. We now want to fit some simple mathematical models to the spectra so that we can start to investigate those lines. So you could go through and do that for all of the lines you find, or you can make selections based on which elements it has found. You can limit to, for example, just the hydrogen lines or just the ion lines. And then all of the other information that's contained in this grid is all of the information from the database. So all of the atomic parameters of the lines and the energy at which you need to give off a light light at this level. And if we just, for example, pick one of the lines there, go to the next part, we then have lots and lots of options of how to fit the lines. So this is with simple normal distributions or Gaussian models, just to model the lines. And that allows us to see how intense the lines are compared to one another and where the central positions of those lines are. So what I've done here is just select all of the dates to plot individually. And we can specify an X range for these plots. So the hydrogen line is quite broad, so we're going to change that from the default. And then we run this and ask if we want to plot the data, which we do. So this is the same line, the hydrogen beta line, but plotted across different observations. So the blue line is the input spectra. And this is where the high resolution data really comes into play. So you can see that the noise around the emission line itself is due to the such high precision that we measure this line in. So again, your human hair that's been cut up probably about 10,000 times in this case. And the red line that you see is the modeled fit to the data. And you can see from that the central position. So again, if you imagine that at 0 velocity, that's where this line should be, accounting for the motion of the star. For us, it should be at 0, but it's actually at about -9 on this date. But on another date, it might be at a slightly different value. So this is again how we start to see how this material is moving around the star. So we can see that on the next page. So this was all the lines that got fitted. It's all the same lines. And this next one, we can plot what's called a periodogram and a phase plot of these lines. So there's only a few data points, and this is what's called a phase folded diagram. So where you have 1 and 2, this is like 2 periods or 2 rotations of the material and how well the data fits. And so it doesn't look bad. This is with the default rotational motion of the star. But again, there's only a few data points here. We can do this for hundreds of data points and build this up across all of the observations we take. At the bottom here, we have what's called a periodogram, and this just looks for periodic signatures in the data. And we can see that there's actually another potential period here, even just with this small data set of about 3.9 days. So if we go back to our input, change this to 3.9 and run it again. Okay, so we now see that the curve fitted behind the data there is actually fitted quite well. So that's where the two plots correspond. So the different colors here correspond to different periods as the observations have been taken. So these data are over a few different years. So there are a few other things you can do with the code. So you can also look at temperatures and densities, which I'll go back to in the other slides. But essentially everything I just went through there is taking the data, which you can get from the database and run all the way through and get to this really detailed analyses and results just in a few minutes, really. Whereas when I first started and we were doing this sort of manually for each star by hand, it could take sort of weeks to months to get to that stage, just to be able to then start analyzing the data. So for the remainder of the talk, I'll go over some of the results that we got by applying StarMelt to some of the archival data and some new data. So this work was all published recently in the monthly notices of the Royal Astronomical Society. And the first star that we looked at was X Lupi, which is the data that I just showed you in the notebook. So this is one of the prototype young stellar objects, like I said before, that has these outbursts that are quite well defined, and it's other stars that have behaved similarly follow this star's example. And what we found looking at X Lupi is that even though it's undergone different accretion bursts and quite variable processes in its disk over the sort of 10 years that we have data for, the periodicity of these emission lines is actually very well constrained across this time. So these plots that you see are like what I showed you in the code. So they're the phase plots showing how the material is moving sort of one way or the other around the star. So the central position of these emission lines. And this is where it really does come down to interpreting the data that we get from the spectra. So these four plots here are of the same emission line, an ionized helium line, but over different date ranges. And you can see that they all look, or some of them look quite different. So they have different amplitudes in this case. So the mathematical fit that you put through the lines there is different on some dates than it is from other. And these corresponds to different accretion processes. So if the accretion is lower, it might be that the region producing this emission is actually a different place on the star, or it's moved further away from the star, or sort of up and down on the star's surface. So that's something else we can look at. The two plots that you see at the top there are, if you imagine that you've taken the star looking straight down from the top and squashed it down into a sphere, then all of the data points that you see on this polar plot is where the emission's coming from, assuming that that is all channeled onto the star through this hotspot. So we can actually see where the spatial locations of different elements are, and if they're all sort of feeding onto the star at the same place, or if some of them are feeding onto stars at different places, that might mean that that material is in a different position in the disk of the star. And again, this sort of goes on to broader questions of how, for example, in the solar system, like we have all of the rocky planets close to the star and all the gas giants further out. But this is something that's actually quite uncommon based on what we've seen so far from all the exoplanets. But could it be that the material, if it's feeding onto the star at different locations, that it's actually in the disk at different locations as well? That's something that we're aiming to look at. Another way of checking this is by looking at the ratios of the line intensities. So before, where I showed you, we can get the central positions of the lines. We can also look at how intense the line is. So essentially, its amplitude, or its amplitude and width, by comparing, in this case, lines that are neutral and ionized. So, for example, helium and then ionized helium. I'm not going to go into all of the equation here, but it uses different thermodynamics and atomic parameters and statistical distributions to essentially say, okay, if we have these two line pairs at a given temperature and density, what should the ratio of these two lines be? We compare that to what we actually see. And what these plots show is these little stars that you see are the best fit regions for density across the x-axis and temperature across the y-axis. So for this one on the right here, this is for the helium lines. We see that we need a very high temperature and density to produce those lines for what we observe. And then the ones at the bottom, these two plots are for ion lines. And the one on the left is for all of the ion lines, and the colors that you see in the background is like the area of best fit. And the one on the right is for five of the ion lines that have the best data. And you can see that in that case, the best fit region is much smaller, much better constrained. So for this good data, we're able to tell with quite good certainty within the assumptions what the temperature and the density is around these stars that's giving off this material. And we can also do that with the same species of lines. So in this case, ion lines that originate from the same upper energy level. So again, without getting too specific, when you have lots and lots of atoms, of elements of a given species, if you assume that there's an equilibrium in a thermodynamic equilibrium, so that there's sort of layers of material at different temperatures, then when all of these emission lines, when the atoms, when they get excited and start giving off emission lines, if some of them have started at the same temperature, you can then you again use some more mathematical models to do the same sort of process and find out what temperature and density you'd need to be able to get this observed ratio. So at the top graphs that you see, lines of constant temperature and density, and the vertical line that intersects all of them is what the observed measurement is. So if we take this pair of ion lines from the spectra and we compare the ratio of one to the other, we get about 0.5. So one line is twice as big as the other line, essentially. And then what the maths does is tell us, okay, what temperature and density do we need to have this line be twice as big as this line? And again, this is where we have so much data for so many stars. We really want to be able to do this as quickly and efficiently as we can, which is what we're able to do now. So the other star that we looked at, doing for time, is GQ Loopy. So this is another young star. And in this one, we looked a bit more at the line profiles. So this is a hydrogen line. And you see on the right here that there's this dip in the line itself. So this is on what's called the red side of the materials. So as if the materials moving away from us. And because it's an absorption, what this corresponds to is that you're actually looking along the line of sight of the accretion channel. So this material that's feeding onto the star is right along our line of sight as we point our telescope to it. And by looking at the extreme speed at which this happens, the speed that this infill material is happening, by comparing that to the properties of the lines, there's actually an anti-correlation between the temperature needed to give off the lines at those regions and the speed at which it's happening. So this is showing us that the material that's falling from furthest away is produced in the lowest temperature, which is sort of what you'd expect. The material further away from the star should be a bit colder. However, this is contradictory to some of the research that had been published before on this. But another thing that we'll look into a bit further. The last star that we looked at in the paper was one called CVSO 109. This one didn't actually have a stellarium input, but a lot of you will probably know exactly where this one is from those three stars and the Horsehead Nebula there. So this is a star in Orion, and it's another young star. And this data was collected in collaboration with some ongoing projects that are monitoring some of these young stars with the Hubble Space Telescope, the Very Large Telescope in Chile, and in some cases, some of the X-ray telescopes as well. So we're actually looking to get a complete comprehensive overview of these stars across all the energy ranges, which isn't what I'll talk about today. However, we did look at the optical and the infrared spectra from the VLT, the Very Large Telescope, of this star, and we only had 4 observations in this case. So the previous data that I showed you was across many, many years. We had hundreds of spectra. In this case, we only have 4. Well, what we did find is across these 4 observations, we seem to have observed the star at just the right time. That in this case, we have a red-shifted emission wing. So for 2 of the observations, 2 out of the 4, there's this excess emission on one side of the line. And because the line itself looks like it has these double profiles, this is something that I didn't talk about too much earlier, but this is suggestive of material coming from the star itself and also from the disk. And because the line profile is asymmetric, this suggests that the material is rotating around the disk and that we actually just observed this star at just the right time to be able to see that. And another thing that we can look at is more of the atomic parameters of the lines. So for the helium lines in this case, and see these atomic parameters correspond to the temperature and the density needed to produce these lines. And it looks like, again, that this varies with the radial distance of the material from the star based on the transition. So we really can tell a lot about what's going on and start to map out these young stars. And work that I'm doing now is we recently had an observing proposal. Well, the observing proposal was accepted a couple of years ago, and then it was postponed due to the pandemic. But earlier this year, we were able to get the data remotely. So I didn't go back to Chile, but we did remotely connect and obtain the spectra for all of these stars. So all the red dots you see are the data that we got. And this is what I'm currently working on now. So analyzing all of these data. And we've got some really interesting line profiles from some of these stars. So this is the work in progress that will see me through for the rest of the contract at Dundee there. And I'm getting towards the end of the talk now. A quick advert for if anyone is in Dundee over the next 2 months. Part of our project with the STFC funding that we received was to work with produce an art science collaboration. So we were working with the artist duo Semiconductor, who have created this really wonderful artistic interpretation of the research we've been doing. So everything that I've just spoke about tonight, they've produced these very clever LED panels that take the input data and change in color and shape based on that periodicity of the data, and then produce some really nice visual images on these LED panels. And this is going to be displayed at the Mills Observatory in Dundee from next week, which is free to go and see as part of the Neon Digital Arts Festival. So if anyone is in Dundee, please go and have a look. And a quick update, as I said, for the HOYS project. So HOYS is the citizen science photometric monitoring program that I know people here do submit images to. And just, I think it was last week or the week before, we actually went past 50,000 images submitted now to the HOYS server. So quite a large milestone. We've also, for the last 2 years, been a Las Cumbres Observatory Global Sky Partner. So last year we sent out adverts for people to get involved. If they didn't have their own telescope but wanted to be part of the project, they could log into the LCO system and take images and submit them to the HOYS server to be analyzed along with everything else. I'm not sure when Dirk was last here, actually, if he spoke about that part. But yeah, and then we reapplied this year and got the funding extended to work with school teachers. So we're doing the same process where we have about 40 or 50 school teachers, I think it is, have signed up, who are going through all the process of accessing the LCO telescopes, taking images of these stars, which are the same stars that I talked about today, actually, these young stars, same sort of science goals, and submit the data, calibrate the data, and produce these light curves of the stars. So we also have a newsletter if you're interested. If you Google HOYS, or the website is actually hoys.space, very easy to get to. You can subscribe to the newsletter to see how that's going. So I'll leave with my summary, which is that yeah, we're actually able to analyze a lot of this data very quickly and efficiently now. We've got some very nice science results, and there's a lot more to be found. So I think, as Mark said in his intro, it's quite a small part of a very wide field, but this is what I've been doing for the last couple of years. So thank you very much again for the invite and listening tonight.
Thank you very much, Justyn. That's fantastic. Thank you. Thank you. Always fascinates me how much you can infer from the tiniest amounts of data that we get. Questions from the hall, from Zoom and YouTube, if you have time. Shall we ask for the hall first of all? Yeah. Any questions in the hall?
Thanks for your talk. It was excellent. Just wondered, have you looked at the sun or anything like that, or anything sort of near at hand that you know a lot about?
Yeah, that's a great question, actually. The solar physics is definitely its own field, and that's because we get such great data of the sun. I mean, both in spatial resolution and spectral resolution. So it's not something that I work on, although there is a research department at Dundee that's doing work on solar physics. However, we did have a collaboration with some researchers at the University of Glasgow who had spectra of the sun, and it was actually spatial. So they took the sort of disk of the sun and they took spectra all over it and were looking for these emission lines. And it was Aurora actually who gave a talk at Glasgow University about a year ago. And the person working on this solar data said, oh, actually the code you've developed could be very useful for this. So I was put in touch with one of their students and we worked together so the code, again, it's publicly available now. At this stage, it wasn't, but we made some small modifications so that they could use it. And yeah, they started looking at the solar spectra in the similar sort of way. So said it is really an advantage that you have that resolution of the sun. And you can see why studying our own star in comparison to all the others is really useful.
Anyone else here?
Thanks very much for your talk, Justyn. That was fascinating. Have you had any results from your researches that have really surprised you?
Surprised me. I think the one I showed at the end where we got this unexpected data, which definitely seemed that it was a good timing event because the data was just over sort of 3 nights, and we can extrapolate on how fast the material might be moving and if we would have caught it at a different time. I think that was just quite lucky. In terms of the surprising, I think I'd like to get back to you on that because I'm sure it has happened, and you get sort of so used to looking at this, you sometimes do have to take a step back and remember exactly what it is you're looking at sometimes, but maybe after if I think of anything.
Anyone else before we go to Zoom? Okay.
Hello, Byron. I think you had a complex question. I shall try and unmute you so that you can talk about it. Hello, Byron. Are you hearing us?
Yeah, hi there. Hello from Bucharest. I was just kind of had a couple of questions, of which the first question was wondering about the different types of stars, because you have sort of high mass stars and low mass stars. And do you see a difference in the kind of data you get as relates to the mass of the stars?
Yeah, of course. So that is one of the science questions driving this, is how the accretion, how the disk changes. So for what's called high mass stars, it is quite different because the physics behind how these high mass stars form, they stay embedded within their molecular clouds and they ionize the surroundings, and they probably have very different accretion methods than your sort of intermediate to low mass stars. But even then, if you take stars like that are around the size of the sun or smaller, it's quite well understood that you have this disk mechanism where the material feeds onto the star through that. And these are what are called classical T Tauri stars. So just a nomenclature for the type. As you go to larger mass stars, to sort of your A and B type spectral type stars, so getting up to about maybe 5 solar masses, 6 solar masses, then it does get a bit more complicated. So I've just skipped back to this slide because when you go to different spectral types, you have very different continua of the overall spectra, which needs to be accounted for. The lines can also be very broad, so it can be a bit more complicated to look at these higher mass stars. And it's also still under debate about whether it could be more of a spherical boundary layer type accretion rather than just through a disk, or some combination of both. So that is definitely something that I'm interested in and that we're looking to answer. But again, this is to be confirmed.
Thank you. The next one was from Sean Wickstead. So I shall try and unmute you.
Can you hear me?
Can hear you fine.
Great. Firstly, thank you very much, Dr. Campbell-White. That was a fantastic presentation. You clearly put a lot of work into it. Those of us watching remotely really appreciate it. I suppose my question really was around how much your work is starting to explain some of the more exotic things we're seeing in terms of planetary formation. I'm thinking particularly around things like brown dwarf stars and how stars that really are literally just at the threshold of, I suppose, what we understand constitutes a star can form planetary systems, particularly where you've got these sort of super Jupiter objects in very close orbit to stars. I don't know if the science is advanced enough yet to maybe begin to explain some of these really sort of odd and exotic kind of planetary systems we're seeing over the classical model we had understood up until now.
Yeah, that's really a great question. I think in terms of my work, it's sort of just before that stage. So there's quite a lot of proposals at the moment with the next generation of telescopes. So this is on the observational side. So we have the James Webb Telescope due to launch soon. And we also have all these next generation of extremely large telescopes, so the 40-meter classes. And they're really going to increase the spatial resolution that we see of these stars to be able to see of these, especially these lower mass stars like the brown dwarfs and the hot Jupiters around those. So the work we're doing sort of just before that, the planets might be forming there. There's one thing that I mentioned during the talk is that these accretion signatures, they can sometimes mask the signal of planets. So where people are trying to find sort of the earliest like protoplanets, almost like just cores of the planets as they're accreting their materials from the disk. This is sort of what might be the next big thing in observational astronomy for this part. So especially with these new observatories that we're getting, and something that I can't give the specifics of, but I do know a bit about from attending conferences and workshops on the subject, is that on the theoretical side, so the simulations, they're making a lot of excellent progress on running computer models and hydrodynamical simulations of exactly what you asked in your question. So the low mass stars, the different kinds of planets you can form. And another area that I'm interested in actually is the synergy between the simulations and the observations, and how you definitely you can't have one without the other, and they do kind of tend to overtake one another based on how quickly each respective technology evolves. So that's something that if you're interested in there, I would definitely have a look at the simulation side of things, and yeah, what we can expect from the next generation of telescopes.
Thank you.
Good, that's everything from Zoom at the moment.
Any questions for YouTube, Bill? Yep.
Good response from YouTube. Just one question which we're offer is from Molten Phoenix. Would it be possible to age pre-main sequence stars using this method, using the amounts of different elements and their positions in accretion disks, etc.?
Yeah, that's a great question, and that is pretty much how we do that. Is one way of aging these stars is by looking at the population of the cluster. So right back at the start of the talk, I said where these stars form in clusters, you can fit your models of the main sequence to the clusters, and stars that are in the pre-main sequence phase are sort of just above the pre-main sequence on the HR diagram. And you can get its spectral type from looking at the high resolution spectra. So this is something that I didn't really cover in the talk, but again, it's a lot of comparing the spectra that you take to computer models. So some of this has only been done through these computer modelings of the different spectral types. So that's something that we did in for the last star that I showed, the CVSO109. So that's not work that I was part of directly, but in the collaboration that looked at that data, that was something they did. They wanted to get the spectral type of these stars so they could pin down the age, exactly how old it is.
It's great. I have a question.
Sure.
Obviously, the HOYS project is photometry using amateur telescopes. If Dirk decided to expand the HOYS empire, could he expand it to amateur telescopes doing spectroscopy like this? Would we have the resolution, the light grasp, and could your star melt software analyze the data from amateur telescopes?
Yeah, that'd be great actually, and I think it's a great advancement of the project. I think the reason we haven't done it so far is one, because the Beacon Observatory doesn't have a spectroscope. I know Dirk's trying to build a new observatory that, or keeps flying for money for a new observatory that does have a spectroscope. And then I'm sure it would be incorporated in such a way. And maybe if this is something that does interest amateur astronomers, I know even I saw from your talk recently that is quite fascinating to take the data in this way. And although it's quite a mathematical way of seeing it on a graph instead of a nice image, I think as well what we can show is that you can get such nice information from it that it might be something of interest to amateurs to be able to submit spectra. So I think it's a definite avenue. In terms of analyzing it, definitely with the code, yeah, it's compatible with, it's very robust. So we've looked at even laboratory-based experiments. This is also at the University of Kent. So they have a light gas gun where they accelerate projectiles at about, I think it's 5 to 8 kilometers per second to simulate impacts onto solar system bodies or spacecrafts with space debris. And they have a very low resolution spectroscope that they take data for that for. And I'm working with the collaborators there who are also using the code the star melt code to look at these spectra. So the low resolution isn't an issue. I think the advantage doing it in HOYS, even at lower resolution, would be the temporal resolution we get. So the same way that HOYS has its advantages with the photometry and that it's taking over a very long period of time, even if we had a lower resolution spectra, but again, taken over a very long period of time, for the stronger lines that are prevalent in these stars, like the hydrogen lines, the calcium lines, seeing how they evolved over time and having the synergy of the photometry already there from HOYS, that would definitely be a great route for the project to take.
There you go, HOYS, Ducky, if you're listening, HOYS 2. Can we thank Justyn again, please? Thank you. We're going to have a little changeover just now, and Alan's going to set up for the sky in November. It's November, isn't it? Yes.
Hello, everyone. Right. The sky in November 2021. This chart may look familiar, but I don't normally show it as a negative. White stars on a black background showing the sky at these times. Let me get my laser.
Can I just say we're not seeing that image?
At these times for beginning. Can I go? Right. You didn't say start. We said it yet. Okay. This is a view of the north and the southern hemisphere of the sky at the times shown here in November, beginning, middle, and end. But this time I've made a negative and showing white stars on a black background. Now, the article that appears on the Society's webpage every month for the month's night sky is largely based on the articles I write for the Scotsman newspaper. And I've been doing those articles now since 1974. You can work out how many years that is. And when I first started to write them, this was how the chart appeared in the Scotsman. It was white stars on a black background. And it was a few years after I started that they switched to doing black stars on a white background. You can tell me which you prefer. Anyway, this month I've decided to be different and show it like this. The views, of course, have the horizon, these horizontal lines at the base of each hemisphere, and overhead is the top of the semicircle. So the constellation Cassiopeia is quite close to overhead in the north at these times. But let's start highlighting the plough. If you've been photographing the aurora recent nights in the evening, then you'll know the plough is now at its low point in the north below the pole star Polaris. And during the course of the night, it winds counterclockwise, climbing through the northeast towards the zenith. And at the same time, Cassiopeia, which is nearly overhead at these times, falls down through the northwest until it's getting underneath the pole by dawn. Bear with me a second. The other thing that you'll know if you've been watching the night sky is that we're losing the summer triangle. It's been high in the south in the evening for many months now, but it's now tumbling over into the west. The stars Deneb, Vega are looking north map, and the star Altair, the third star on the summer triangle, is dipping down towards the west, but on the south map. So the summer triangle straddles the boundary between the north and the south. The square of Pegasus, meantime, is coming up to the meridian. Not terribly bright stars in the square, but it's quite empty. A test of how clear and dark your sky is to count the number of stars inside the square. And of course, you can use the square for finding the famous galaxy M31 in Andromeda. Take a line from Alpheratz at the top left corner of the square, go along more or less level with the horizon at these times to the middle star of Andromeda, and then make a right, and pretty soon you reach the hazy patch of M31, the Andromeda galaxy. We have a number of planets visible. At these times, the brightest planet and the brightest object in the sky, if the moon's not there, is Jupiter, but it's now edging towards the west from the south. Much lower down at these times is Saturn. There are two bright planets at this time in the evening. We do have a couple of other fainter planets. One of them is Neptune below the square of Pegasus, and the final one is Uranus over here in Aries to the north and west of the constellation of Taurus. And talking about Taurus, there it is. It too straddles the north-south line, that horizontal line, that semicircular line. Start looking at the solar system, the sun. These are the ephemeris data for the sun for the month of November. The things to look at, of course, are when it gets dark, and you can more or less count that as nautical twilight times, at the beginning of the month around 6 p.m. in the evening, and at the end of the month, more like 5:15 or so. So we have effectively more than 12 hours of darkness, effective darkness every night. We see during the course of a November night the full range of the stars. We can see the summer triangle still in the evening, and the stars around the summer triangle. So the best of the summer skies is still just about there in the early evening. And during the course of the night, after you've seen Pegasus cross the southern sky, then you see Orion rising in the east, and we have by dawn, during the morning hours, the best of the winter sky, Orion and the other constellations around it. As far as the moon goes, there are the phases of the moon this month. We're now just past new moon phase, so the sky is dark. A good time if the sky is clear for doing some dark sky observations. And on the 19th of November, we have a full moon, and we also have a partial lunar eclipse. But before I get round to that, I want to go back to the sun, because the sun's been picking up in activity. This was the view of the sun on October 28th, as observed from the Solar Dynamics Observatory, which is a spacecraft in an inclined geosynchronous orbit. So it gets a steady view of the sun, except for a few hours, for about 1 hour a day for a few weeks in the year. Now, around October 28th, the sun was the spottiest it's been for more than 5 years. So, as you might expect, it's a good trigger for possible aurora displays. And sure enough, we had an aurora display a few days later. Fran Goodman of the ASE obtained this nice shot from Aberlady Bay in East Lothian on the 31st of October. And there have been other displays, as you may have noticed, in the past week. Well, back to that lunar eclipse. There's the data for the eclipse for Edinburgh. The moon at the time of the eclipse is in Taurus. It's 7 degrees below the Pleiades in our morning sky, and the eclipse occurs in our morning twilight. In fact, it begins at 6 when the moon touches the edge of the Earth's outer penumbral shadow. At that time, the moon is 13 degrees high in our western sky. The sky is still dark then, but you probably won't notice any fading of the moon until the moon gets closer to the central dark umbra of the Earth's shadow. And nautical twilight begins at 6, and civil twilight at 7. But the moon doesn't start to touch the umbra until 7. And by that time, the moon's only 4 degrees high in the west northwest, and the sky is getting quite bright. And the moon sets at 7:49 when it's 40% of the moon's diameter into the umbra. And the sun rises for Edinburgh at 8:02. So we don't get a very good view. If you've got a clear horizon to the west or the west-northwest, just at dawn, it's not too early in the morning, then it might be worth looking out and see if you can see the moon and see if you can detect some trace of the eclipse taking place. Of course, if you're further west, in fact, in the whole of North America and most of the Pacific sees the entire eclipse from start to finish and should have a good view. Perhaps we've got some viewers of this program in that area. We can look forward to that. Okay, the planets. This is the banner showing the 360 degrees of the sky. The sun is in this bit of the sky, tracking through Libra into Scorpius this month. The area to the east of the sun is the evening sky. The area to the west is the morning sky, and the area which is flagged as opposition is 180 degrees away from the sun. Well, looking at the planets this month, Jupiter and Saturn are now in the evening sky, and that's the same. The pictures of those two planets, relative size is correct for November the 16th. Jupiter quite large, Saturn nearly as wide, including its rings, nearly as wide as is Jupiter. But the other planet in the evening sky I haven't mentioned until now is Venus, which is quite low and is set by those 8 p.m. middle of the month charts that I showed earlier. And you'll see that by the end of the month, Venus is getting bigger in terms of diameter than Jupiter. Of course, it's a lot smaller planet, but it's a lot closer to us. It's also brilliant at magnitude -4.4 at the beginning of the month, and the beginning of next month, it's got to -4.7. So it's improved in brightness, it's got brighter. Venus was furthest from the sun, 47 degrees from the sun on October 29th, but it's been further south than the sun all this time, so it's been very, very low in our evening twilight, and you may well not have seen it, particularly if you've got pendulums in the way as I have. There is another planet in the morning sky, and that's Mercury, but we're losing that now. It's coming to the end of its best morning apparition for 2021, and it's disappearing into the sun's glare in the next few days, and it's reaching superior conjunction on the far side of the sun on the 29th of November. And the other planet, the naked eye planet, is Mars, which was in conjunction with the sun on the sun's far side in early October and becomes visible very low in the southeast just before dawn later in November. And the final two planets, so those two objects, Neptune and Uranus that I'll come back to later. This is a view looking north at 8 p.m. or 20 hours GMT in the middle of the month. You see here the plough, okay, yeah, the plough below Polaris in the north. You'll see Gemini and Taurus rising in the northeast to the east. Capella, the bright star, which has been low in our southern sky during the summer, now climbing in the northeast, and there's Cassiopeia near the zenith. Now, and Draco, the constellation of Draco, the dragon, winds between the Polaris and Ursa Major, and it's at its head, the head of Draco, a few degrees north of Vega, the brightest star in the summer triangle. Now, if you've been reading our newsletter, and I know you have, then you'll know Mark has been encouraging us to take a look at the Garnet star, Mu Cephei, and that's where it is. It's very near the zenith at these mid-evening times. There is a picture taken by Mark of the star. It's got the name Garnet Star from Sir William Herschel, who named it such in 1783 and described it as a very fine, deep garnet color. It's a red supergiant or even a hypergiant star with an energy output about 100,000 times that of the sun, and it's around 10 million years old. The distance is very uncertain. It's given variously as between 1,200 and 3,000 light years. And it's also variable between magnitudes 3.4 and 5.1. A naked eye star, and at the moment it's near the top of its range, about magnitude 4.0. This is the view west at the same time. Mu Cephei being near the zenith is near the zenith on this chart too. But here you see the summer triangle. I'll just highlight it. There's a summer triangle. Still the summer triangle high in the south at nightfall, but it sinks towards the west by these times. Lots of interesting objects still on show around the summer triangle, including the Ring Nebula in Lyra, the Double in Lyra, the Dumbbell Nebula in Vulpecula, right in the middle of the summer triangle. We can also see the two planets I'm going to come back to, Jupiter and Saturn, in the southwest. They're not, as I say, our only bright evening planets, because Venus has been lurking in our very low evening twilight since the beginning of the summer, but at last it's climbing a bit higher. This is the view the Stellarium gives us for 30 minutes after sunset from Edinburgh on November the 1st and December the 1st. This line is the line at 20 degrees altitude, and the one below it is 10 degrees altitude, and you can see Venus is heading southwards at these times and getting slightly higher. It was 4 degrees high half an hour after sunset on November the 1st, and by December the 1st it'll be twice as high, 8 degrees high, as seen from Edinburgh. It's also getting closer to us. It's approaching from 97 to 64 million kilometers as it's getting towards the near side of the sun, and there again are the appearance of the planet on these same dates. So it's roughly, at the beginning of the month, it's roughly 50% illuminated, or 48% it says, illuminated on the 1st of November, but by the end of the month it says 48, but it's not, it's less, 30 or something. That's because it's coming around the near side of its orbit, and it'll pass 5 degrees north of the sun on January the 8th at inferior, as it reaches inferior conjunction. On the 7th of November, which is Sunday evening, on the 7th of November, then this is the view at the same time, half an hour after sunset from Edinburgh, and there's Venus. The 10-degree high mark is here. So Venus is there, and the moon is also visible to the right of Venus, and the moon is 11% sunlit on that night. That's the view. The following night, the moon has jumped over here to the left of Venus, and it's 20% sunlit. And between those nights, the moon more than doubles in brightness. So this is looking south now in the mid-evening. Note on the 16th of November, the moon is fairly prominent. Just if we can ignore it for now, we will. The summer triangle is over here towards the west, square of Pegasus in the south, Andromeda going off eastwards. M31 is, well, you probably won't see it on this diagram, but it's just there. Below Andromeda's triangulum, the triangle Aries and Pisces winds around the lower left corner of the square of Pegasus. For now, though, I'm going to concentrate on this region, which includes the bright planet Jupiter. Here it is. There's Altair. A line from Vega through Altair points to Saturn, which is in the constellation of Capricornus, and also in Capricornus is Jupiter. They're both moving now eastwards in the constellation. That's the tracks of the two planets during the course of the month. Well, in fact, from the 1st of November to the 16th of December, a month and a half. And there is Jupiter again, magnitude minus 2.4 and 40 arc seconds across. And there's Saturn, magnitude 0.7. So a good deal fainter, slightly brighter, just a bit brighter than Altair. Radim Stano, or one of our European members, has produced this image of Jupiter and its moons Ganymede and Io, taken on October the 16th. And Mike McGovern had this photo of Saturn on the previous day, October the 15th, and you can see in his photograph of Saturn how the shadow of the globe of Saturn is falling on the rings to the left, the eastern edge of Saturn. You can see a gap there. The rings don't join on to Saturn as they do on the other side of the disk. Okay, let's look at the moon relative to Jupiter and Saturn. This is the view of the position of the moon on the 10th of November. On the 10th of November, next Wednesday, next Wednesday, it's below and left of Saturn, and it appears like that, 42% illuminated. And a day later, on the 11th, on Thursday, it's closer to Jupiter and below and left of Jupiter, and it's 53% illuminated as per such. Back to our wider view of a southern sky, and I want to concentrate on this area south of the square of Pegasus, including this pattern of stars we call the circlet of Pisces. There it is in this close-up, and alongside it is the water jar of Aquarius. The water carrier is carrying a jar of water which he's spilling, but that's the water jar. And here below the circle of Pisces is the planet Neptune, and there's a picture of Neptune, or Stellarium's view of Neptune on the 16th. On that date, it's 4,410 million kilometers away, which means its light time is around 4 hours, 5 minutes. So we see it as it was more than 4 hours ago. And Mike McGovern took this image of Triton, of Neptune during this few days recently. I haven't got the date there, I'm sorry. Triton, the largest moon of Neptune, is magnitude 13.5. So it's quite dim, but it's interesting in that it was discovered by the English astronomer William Lassell on October the 10th, 1846, which is 175 years ago. Is that right? Anyway, it was discovered 17 days after Neptune was discovered. It takes 165 years for Neptune to circle the sun. Triton is, and there's a view of it from Voyager. Triton is the 7th largest moon in the solar system, and it's the only one in a retrograde orbit. It's just a bit smaller than our moon. It's thought to be very similar to Pluto in composition, having been a dwarf planet at one time in the Kuiper belt. Neptune has 13 other much smaller moons, but if you want to see them, you've probably got to go there to catch them. This is the view east at the mid-evening time, and I'll point out Taurus and the Pleiades above the eastern horizon, and to their above and to the left is Auriga and Capella. Here's Andromeda with Triangulum and Aries. There's a circlet of Pisces more or less in the south, Cassiopeia overhead. Of course, there is a myth that connects Perseus and Cassiopeia and Andromeda and Pegasus. Well, Perseus was riding Pegasus with the head of Medusa, one of the Gorgon sisters, which he cut off when he encounters Andromeda by being threatened by Cetus, the whale or the sea monster. And he slays Cetus and rescues Andromeda and rides off on the back of Pegasus, something like that. Orion is rising down here. Just see the head of Orion poking up in the east, well to the right of Gemini, where you have Castor directly above Pollux as they rise above our horizon. But the area of interest now is this one, taking in bottom of Perseus and Triangulum and Aries. Let's take a look at that in close-up. And that has got in it the planet Uranus, the second most distant planet. It's retrograding. In other words, it's moving westwards in the sky to the right as we look at it. And there is its dates between November 1st and December the 16th. It was at opposition yesterday when it was directly opposite the sun in the sky. So at its closest, it was 2,803 million kilometers away. That's the representation of Stellarium's view of Uranus at this time on the 16th of November. I don't think you can probably see, well, some people at home may be able to see it on their screens, but probably not in the room. There is a trace around Uranus of the ring system that Uranus has. But again, you probably got to go there to see it properly. There are the 5 main moons of Uranus. Oberon and Titania are about 40th magnitudes. The other ones are fainter down to Miranda, which is only magnitude 16.4. Back to a wider view in the east, and let's concentrate on this area, taking in Auriga and Taurus. And I want to pick out a couple of moving objects here of interest. One of them is comet Schwarzmann-Wachmann, which is moving along this trajectory during November is moving from Auriga into Perseus, I think it is. Yeah, Auriga to Perseus. It's thought to be a giant comet. It's thought to be about 60 kilometers in diameter, its nucleus, which is big for a comet, but it moves in an almost circular orbit between the orbits of Jupiter and Saturn. It takes 14.7 years to go around the sun. It's normally around magnitude 15 or 16, but it has around 7 outbursts a year when outgassing events occur, and it produces its nucleus brightens up, and a coma develops for a few days. And it's currently been enjoying several quite bright outbursts, and it was reported at magnitude 10.7 last night. So it's well within range of amateur instruments. And this was a photograph taken on October the 30th of the comet, showing this is where the nucleus is, and the outburst has produced a coma of material, of gas and dust surrounding it. The other object I want to pick out is Ceres, the minor planet Ceres. In fact, it's a dwarf planet Ceres, which is currently passing through the Hyades cluster. So if you've got any pictures of the Hyades recently that go down to magnitude 7 or 7.5, then take a look out, see if you've caught the dwarf planet Ceres. It's magnitude 7 to 7.5, and it's going to be brightest at opposition on November the 26th, 27th. I think more or less at midnight on November 26, 27, when it'll be 264 million kilometers away. Of course, it was visited by the Dawn spacecraft in 2015. There's an image, a NASA image of Ceres, well within range, of course, of binoculars. Now this is turned back to the south, but later in the night. This is at midnight on November the 17th, 0 hours on November 16, 17, if you like. Orion is well visible now. It's well clear of the horizon. It's in the southeast. Below Aldebaran and the Pleiades, a line through the belt of Orion stretches up to Aldebaran and the Pleiades, and if you take the line the other way, you get to Sirius, the brightest star in our night sky. Capella is nearly overhead. As Orion reaches the south, you'll always look for Capella in Auriga, and that passes overhead. But let's concentrate on this region. This is a region of interest because a couple of things I want to pick out here. One of them is Sharpless 261. Now, I don't think any of our astrophotographers have taken a picture of this yet, but I've put it in. It lies in the club of Orion. Here's Orion's club. There's his shield, and this is Orion's club being wielded above a shoulder star, Betelgeuse, the red supergiant. Well, that's what Sharpless 261 looks like. It's also called Lowers Nebula, after the father-son amateur astronomers who drew attention to it in 1939. They photographed it with an 8-inch Schmidt telescope they'd made themselves. There are various distance estimates for it, between 1,000 and 2,400 light years. It's around 30 arc minutes north-south. That's about the same size as the moon. It's quite faint, but it's certainly within range of our astrophotographers. It's not a Messier object, and it's not in a Coldwell catalogue, so there's no great incentive to photograph it. But I'm glad this Dean Salmon took this picture. Well, well, it wasn't Dean who did it. It was Dan Bartlett who took this picture. This was a view of it on October the 3rd, a month ago. And there's the nebula. There's Lowers Nebula, Sharpless 261. And here's a comet, Comet Faye. Comet Faye was discovered 178 years ago. It's called Comet 4P Faye because it was the fourth comet to have its orbit, fourth periodic comet to have its orbit calculated. It was discovered in 178 years ago in 1843 by Hervé Faye at the Royal Observatory, but one in Paris. A small comet, 3.5 kilometers wide, orbits the sun every 7.55 years. It comes to perihelion at 249 million kilometers from the sun. That's the outer edge of Mars's orbit. And Nick James of the BAA has an excellent article about the comet on the BAA's webpage for the comet observing section. If you do a web search for the BAA comet Faye, then you'll find all the information about this comet. It was the fourth comet to have its orbit calculated. The first was Comet Halley. And I know that comet, that calculation was done by Thomas Henderson here in Edinburgh in 1844. When it was recovered on its next orbit in 1850, though, it was spotted from Cambridge with the help of a prediction by the French astronomer Urbain Le Verrier, who had been responsible for the prediction that led to the discovery of Neptune in 1846, as I said. Perihelion of Comet Faye was on September the 8th, so it's fading now. It's currently about magnitude 11.5 near the Monoceros Gemini border. Now, can I advance? And this was the view on October the 4th. And you can see it looks as though the comet's Faye has been swallowed by that Lowers Nebula, a bit Pac-Man-ish, if you like. The tail, if some of you may be able to see, the tail is stretching off to the edge of the photograph to the right. And that's the path of Comet Faye for November to December. In fact, it extends to, in this case, to every 10 days to January 10th. And I think during that period of time, it'll be about magnitude 12. Now, I mentioned the Lowers Nebula, the Sharpless object was a bit like the Pac-Man Nebula, and by coincidence, I think, This is an image taken by Ian Smith just last night of the real Pac-Man Nebula, which is northern Cassiopeia. It's an emission nebula around 9,200 light years away, and it contains a young star cluster just about there, which is 3.5 million years old, and it's got several black globules, Bok globules they're called, in them, which are dense in the nebula, which are dense clouds of gas and dust in which new stars may be in the process of formation. Now then, I've wound the clock even further forward to 6 o'clock in the morning on November 17th. It's less than 30 minutes before the start of nautical twilight, so there is in the south or the east, the southeast, you can see a glow in the sky, which is sometimes called the false dawn. This, of course, is the zodiacal light particles in the plane of the solar system scattering sunlight. In the south, well, Orion by this time is heading off towards the western horizon, but in the south you have the constellation of Leo, which has Regulus, the brightest star in the handle of the sickle of Leo. And it's in the sickle of Leo that we have the radiant for the Leonids meteor shower. Meteors from this shower appear in all parts of the sky. The details for the shower are there. The shower is in fact active from more or less tomorrow to the end of the month, but its peak is around the 18th, and you won't see very many Leonids meteors except around that time. The peak, though, is this year thought to be only about 15 meteors per hour, so it's not a very active shower. The meteors, though, are unusually fast. I think they're about the fastest of all the meteors, 71 kilometers a second. They come from comet Tempel-Tuttle, which orbits the sun in a period of 33 years. And they were impressive Leonid showers, even some of the meteor storms, when it was last near perihelion in 1966 and 1998, 99. So we're probably not due another one until 2033 or so. But sadly, this time, as you'll see, moonlight is quite bright around this date. So even if you do get Leonid meteors, all but the brighter ones will be swamped by the moonlight. Let's look to the west of Leo to highlight another area, this one, which takes in the area around Gemini and Cancer. And there is another comet to think about, comet 67P Churyumov-Gerasimenko, usually Gerasimenko. You can hold applause. Anyway, it's heading eastwards as it's positioned on November the 1st, and quite close to Castor and Pollux, and it's heading eastwards to northern Cancer. It's famous, of course, for being accompanied and explored by ESA's Rosetta spacecraft, which spent around 2 years near the comet between August 2014 and September 2016. And it ended the mission by deliberately crash landing on the comet. It returned lots of images like this one of the comet, and was able to watch it develop and outgas and become a true comet as opposed to an icy nucleus. That was, of course, one orbit of the comet ago. Of course, the Rosetta also released the Philae lander, which tried to land on the surface, and in fact did touch down, but then bounced into the shadow of a cliff. So we didn't get as much data from it as we hoped we might. As far as the comet goes, that's its track. It's fading probably during the course of this period between November the 1st and January the 10th, from about magnitude 10 to magnitude 11. Perihelion is or was at 168 million kilometers from the sun on November the 2nd, and it takes 6.4 years to orbit the sun. So this is the first return since Rosetta explored it, visited it. This is a photograph taken by Mark Phillips of the comet. I'll not risk trying to pronounce it again. That's a photograph taken by Mark on October 14, 15. During the course of that time, of course, the comet is moving against the stars, and this is the stars are appearing as dashed lines or dotted lines, as lines on the image, as the comet was sort of fixed in the frame is another comet of interest, and that's comet 2021 A1, Comet Leonard. It was discovered from Mount Lemmon in the USA on the 3rd of January the 3rd of January this year, hence its designation of 2021 A1. A means it was found in the first fortnight of the year, and the 1 means it was the first comet to be found in that fortnight. So it's the very first comet to be found in that fortnight. And it's at that time it was out at Jupiter's orbit, heading sunwards towards perihelion exactly a year later on January 3rd, 2022. So it will be then 92 million kilometers from the sun and inside Venus's orbit. And if you know anything about comets, you'll know that predicting the magnitudes of comets we've never seen before as they approach the sun is always a dangerous pastime. And where we can make guesses, it is currently magnitude 10. By the end of November, beginning of December, it may be magnitude 7. And by a few days later, on December the 9th, it may be magnitude 5, and it may be at its brightest at magnitude 4. But of course, some comets we've hoped would do brighten like this, and they've just fizzled out altogether and broken up. On this journey, it'll be 35 million kilometers from the Earth on December the 12th, which is why its motion appears to accelerate as it gets lower in the eastern sky before dawn. This is looking east at 6 o'clock in the morning in the middle of the month. Perhaps at magnitude 4, but I say beware. It also passes quite close to Venus on 6 days after it passes close to the Earth. I think it was December the 18th. It'll be 4.2 million kilometers from Venus. Its orbit suggests that its orbit suggests that it will last visited the sun 80,000 years ago. So it gives the sun confidence that it's not going to break up because it survived its last passage past the sun. But on this journey through the solar system, it's going to gain energy. So as it leaves us, it'll never come back again. It'll be accelerated out of the solar system altogether. This is a photograph taken about 9 hours ago by Martin Moberly, a British amateur astronomer. I'm guessing he's using a telescope remotely to get this at 11:36 UT today, but that's what Comet Leonard looked like earlier today. So it is looking like a comet, and hopefully we will be impressed in a few weeks' time. The planet I haven't mentioned much before now is Mercury, which this is the view looking eastwards or between east and southeast, 1 hour before sunrise on November the 3rd. That was back on Wednesday morning. And at that time, the moon was 6 degrees above and right of Mercury. And the moon was only 4% sunlit. So there was a good photo opportunity there. Mercury will be visible for a few more days as it slips lower into the twilight as it heads towards superior conjunction on the sun's far side. These are views on November the 1st and November the 10th. The 10-degree altitude mark is this line here. There's Mercury above and to the left of Spica, and by the 10th of November, it's wound on to be more or less on the horizon 1 hour before sunrise. And if you look carefully, you might perhaps see right alongside it is the planet Mars. So it's falling into the twilight. It'll reach superior conjunction Mercury on the far side of the sun on November the 29th. And on this date, November 10th, it's 1.1 degrees north of Mars. On December the, there's the data for Mercury, quite small, becoming fuller in phase as it moves around the sun's far side, and not changing very much in brightness from magnitude minus 0.8. So it is quite bright in the twilight, and should be visible, has been visible to the naked eye. On December the 1st, well, Mercury is gone, but Mars is becoming higher 1 hour before sunrise, still not standing out, and because Mars is a good deal fainter than the magnitude 1.6, you'll probably need binoculars to catch it in the twilight. Mars's visibility will slowly improve until it reaches its next opposition, which occurs in the constellation on Taurus on the 8th of December next year. or a year's time. On that day, Mars will be in Taurus and quite close to the full moon. That's a view of Mercury. Can you see it? It's just there. Mercury in the morning twilight view from Kent on October the 28th by Paul Sutherland. And that is the final slide for this show. Thanks.
Thank you very much, Alan. There's a lot going on in the sky at the moment. That's pretty much it for tonight. That's fine. No, it's okay. So our next meeting is on the 19th of November, and that will be the famous David H. Levy. I'm sure you've heard of him, famous for comet discoveries, amongst other things, and it'll be about his life in astronomy. But I think he's also got an interest in literature as well, in literature and poetry. So I think that should be a fascinating talk, and that will be purely online, so Zoom for members, and visitors are all welcome on YouTube. But there's tea and coffee afterwards, so hang around, have a chat. It's been great to see so many of you tonight as well.